Okay, everyone, we're on page 41, and I'm excited for this topic. It's the second to last topic, and the hard work that you put in for topic 1.6 is really going to pay off here, because this is everything to do with periodic trends, and what we learned in topic 1.6 is the justification for why all these trends work and happen. So I'm going to jump back to this page quite a bit, just as I'm like writing these trends down, so just keep that in mind when you see this periodic table. I'm going to add each trend to this periodic table. So the first one and the most important one is atomic radius. And what's interesting about atomic radius is like, yeah, we know that it's in general, like the way we think about it is the distance from the nucleus to the valence electrons, right? To the outermost electrons. But do you understand that that's kind of a hard ask to actually know where those outermost electrons are, right? Like these orbitals are areas of high probability, like where it's likely that we're going to find an electron, but we don't know for certain like where those electrons are exactly at like given points in time. And so an easier way of doing this is by measuring the distance between the nuclei of two atoms and then dividing it by 2. Now, no, it's not perfect, and the idea holds still, but that's how chemists really measure atomic radius, is they'll take 2 chlorine atoms, right? They'll take a bunch of the same type of atoms and put them right next to each other. And then they're going to look at the nucleus, which is way easier to see than some tiny electron that's whizzing around. So they'll look at the nucleus, and they'll say, okay, this is the distance between those nuclei, and then they divide it in 2 to get the atomic radius. Okay, so for all intents and purposes, just know we're talking about this concept, but that's the actual form of measurement for that. Now, with atomic radius, there's 2 different ways that we can look at radius. It's going down a column or going across a row of a periodic table. So what I mean is, like, here's my groups or my columns, and there's a trend for atomic radius either getting bigger or smaller as you go down a group, and there's also a trend either getting bigger or smaller going from left to right within a row. And we did this, if you want to go back and look at the notes that we took for topic 1.6, we discussed this radius quite a bit, and I very purposely chose examples where it was either in the same row or the same column. And so when on a free response test, when you're explaining these trends, it's really important that you don't justify the trend using the periodic table, meaning you cannot just say, I know that the radius of potassium is going to be bigger than sodium because going down the group, the radius gets bigger. That's not going to work on these free response questions. You have to justify why that's happening, and that's what we're going to talk about. So please keep in mind that when you're explaining the periodic trend, that you need to talk about the atomic structure of the atoms. This could be protons, neutrons, electrons, and energy levels, shells. All of those are atomic structure things, right? Protons, neutrons, electrons, electron shells, all of that is great to talk about when addressing atomic structure. And then the second thing that you really should add to this is Coulomb's law. Reminder about what Coulomb's law is. Coulomb's law tells us that either the force of attraction or repulsion between 2 charged things is equal to this constant, we're not worried about the constant, the charge of one of the things times by the charge of the other thing divided by the distance between those charged things squared. So if we have a positive and a negative, like the positive nucleus and the negative electron, the greater the charge of that nucleus, the greater the attraction to the electron. Or another way of thinking about it is the smaller the distance between the nucleus and the electron, because it's in the denominator, so the smaller the distance, the greater that attraction. And so you can use Coulomb's law to justify as well. One way that I like to do this is by saying this force of attraction and then using this symbol. And this means that it's in relationship with. It's not exactly equal to it, but it's proportional or directly proportional. Like it has a relationship to the charges and the distance squared in the denominator there. And that removes this weird constant that we're not worried about, that we're using it to understand the force of attraction. We're not actually calculating with this equation. So we say, okay, this force of attraction, when one of the charges is bigger, like the nucleus has more protons, then the force of attraction is greater. Or if the distance between the nucleus and electron is smaller, it's closer to the nucleus, then the attraction was greater. All right, so address atomic structure to explain the trends, and use Coulomb's law when asked to do so, because sometimes questions will directly ask for it. Okay? So if you do not write your answer in terms of attraction, repulsion, or energy levels, you will not receive credit. And like they really are explicit. Like they will tell you, and give me an answer addressing atomic structure or using Coulomb's law. So make sure you read the question. You don't just talk about the trend, you explain it. Great. So let's talk about this for a second. What happens to the radius of an atom as we go down a group? Like going from beryllium to magnesium. Okay? Well, here is our energy levels. Like it's how many electron shells these atoms have. Okay. And so if I'm comparing, like let's do beryllium and magnesium. Beryllium has 2 electron shells, and we see this in its electron configuration of 1s2, 2s2. We got 2 electron shells there, where magnesium has 3 shells, 1s2, 2s2, 2p6, 3s2. So this additional shell makes the radius bigger. And that's what I would talk about when describing atomic radius going down the group. I would say how many electron shells each of those atoms have, and then denote that the greater amount of shells results in a larger atomic radius. So as we go down a column, we increase in atomic radius. And this is due to the fact that we are adding energy levels or adding electron shells. Okay. I think Bohr models are really helpful as well, like we were doing before. Beryllium, for example, has 4 protons, and we said that it had those 2 energy levels. Okay. And we can draw our electrons in there. And our magnesium, which is in the same column, but it's just below 1, it had 3. So let's see. Magnesium has 12 protons in its nucleus. First energy level, second energy level, and then our third energy level. The first energy level has 2 electrons, the second energy level has 8 electrons, and the third has 2 electrons. Same number of valence electrons because they're in the same group. And so even though magnesium has more protons, which means that it's pulling on the electrons with a greater force of attraction pulling it in, due to the fact that we added a whole nother shell, the radius of magnesium was still bigger than beryllium. Okay? That the additional protons could not outweigh the fact that we have a whole nother shell, that the overall radius of magnesium is larger than beryllium. And as we go down the group, this will be the case. We have barium, which has 6 shells, and it's going to be much larger than calcium, which only has 4 electron shells. Okay, great. Now, if we're talking about going across a group, I want you to notice that that means any of these in the group have the same number of shells. In this case, it would be 4. And any of these atoms have the same number of shells. It would be 5. So we're dealing with the same amount of shells, so there's no adding of another shell to make it bigger or smaller. The main difference is the number of protons. So when we're talking about going across the row, I want you to, in your free response, I want you to indicate that they have the same number of shells. Same number of electron shells. Okay, so we're saying, look, they both have 2 electron shells, but one of them has a greater number of protons. Okay, this greater number of protons would mean that it has a greater effective nuclear charge, or sometimes they just called it nuclear charge. AKA, it pulls on them stronger. The nucleus pulls on the electrons more strongly. And then our last thing, if it asks, like this alone is great, but if it asks you to include Coulomb's law, then do exactly that. Say this force of attraction between the nucleus and this electrons are greater due to the fact that one of the atoms has a higher number of protons. The charge of the nucleus is larger, and so compared to the other one, right? So we have the charge of a nucleus and attraction to electrons, which then can decrease that distance as well. Okay. All right, great. Quick example though. Let's go boron and oxygen, okay? So boron has 5 protons. It's got 2, there's our nucleus. It's got 2 energy levels. In the first energy level, we got 2 electrons, and then in the third energy level, we got 3 electrons. Write out the electron configuration if you need to see all that. 1s2, 2s2, 2p1. Okay. Then we're going to compare it to oxygen. Oxygen has 8 protons, more protons. It also has 2 energy levels. They're both in this second row, which means that they both contain 2 electron shells. But due to the greater number of protons, these shells are pulled in tighter to the nucleus. There's 2 electrons in the first shell, and then for oxygen there would be 1, 2, 3, 4, 5, 6 electrons in the outer shell. 6 electrons. And so the protons, these 8 protons, can pull on all these electrons far more than 5 protons can, making the overall radius smaller due to the fact that it has a greater number of protons. So the trend is going from left to right. Even though the mass is getting bigger, the atomic radius is getting smaller because it's it's same number of electron shells, greater number of protons, which means it's pulling on the electrons more tightly. All right, lovely. Let's keep on. We also talked about this. Why are cations smaller and why are anions larger? So cations remove electrons. We had the example of sodium. So like sodium has 11 protons. And when it's neutral sodium, there is 3 energy levels when it's neutral. Okay, so sodium. And this electron configuration would be 1s2, 2s2, 2p6, 3s1. So the first energy level has 2, the second energy level has 8, and then the third energy level only has 1 electron in there. Now, what if it becomes a cation? What if it becomes Na+? The only thing that we lost was this furthest electron, the 3s electron. So my number of protons stayed the same, and we no longer have a third energy level. But another interesting thing happens. Whenever we lose electrons, the other electrons get pulled in tighter. So we have the same 2 electrons on the first energy level, 8 on the second. Okay. Now, here's why it's so interesting. This electron, the same with all the other electrons, they're repelling each other. This guy is pushing all of the other ones away. Okay? And so if we remove the thing that pushes them away, then the rest of them can pull in a little bit tighter. So when you're going from neutral to a cation, the radius always gets smaller. Now the opposite is true for the anion, right? That when we gain electrons, then we could be adding energy levels, maybe not, but we're adding more electrons that repel the other electrons, making the radius larger. So same idea as this one, but in reverse, that when we gain electrons, the radius increases. And the reason why is because the additional electrons repel the other electrons. Making the overall radius larger. So if we add more electrons in there, those additional electrons are also going to repel all the other electrons, pushing everything away from each other and causing the radius to increase. Okay, great. Reminder that the term isoelectronic just means same number of electrons. Not the same number of protons, not the same number of neutrons, same number of electrons. So all of these, nitrogen 3 minus, oxygen 2 minus, fluorine minus, sodium plus, and magnesium 2 plus, all have this exact same electron configuration. And guess what? We can see it. Nitrogen, when it's neutral, has 7 protons and 7 electrons, but then if it's a 3 minus, then we gain 3 more. 1, 2, 3. So it's isoelectronic with neutral neon if it gains 3 electrons. Oxygen 2 minus, gaining 2 electrons, same deal. Fluorine minus, gaining 1 electron. And then we can go the other way. Not lithium, sodium. If you lose 1 electron, then it goes from having 10 electrons to 10. Right? So they're all isoelectronic with each other. Okay. Do note, though, that cations are like substantially smaller than their neutral version, and anions are substantially bigger. And so if I'm choosing between like neon, like neutral neon, and we're going to compare that to like sodium, and then also let's do like an oxygen 2 minus. And let's talk radius right now. So sodium has 11 protons, neon has 10 protons, and we know this greater number of protons would pull it in tighter. And in addition to that, it's lost an electron, and we know when we lose electrons, it gets even tighter, even smaller. So this would be our smallest radius, and then neon would have a bigger radius. Now, same idea. Neon has 10 protons. Oxygen only has 8 protons. And so these 8 protons can't hold on to that same number of electrons as tightly. So for that reason alone, oxygen is a bigger radius than neon. But then we also know that this addition of electrons pushes it even further. And so this is oxygen, this anion, is definitely a larger radius than the neutral. So this would be our largest radius if I'm comparing those three. Okay, we'll leave these to do as examples in class. Now, ionization energy is how much energy it takes to remove an electron from an atom. And if it's the first ionization energy, then it's removing an outside or a valence electron. Okay? So when we're not talking about this trend in ionization energy, we're talking about the first ionization energy, the energy it takes to remove an electron from the outside shell. Okay? And it's going to be the exact opposite of what the radius was. This should make sense because as we go down the group, we know the radius would get bigger. Okay, so when you're talking about ionization energy, the first thing I want you to talk about is radius. Okay, for both of these, you were talking about radius first. In this case, going down a column, a group, the radius increases. Like we've discussed, this is due to a greater number of electron shells. Well, we also know that according to Coulomb's law, that, let's do that a little similar, Q1, Q2 over R squared, that if this distance increases, right, if the radius is bigger, then the force of attraction is weaker. So when the distance increases, the attraction decreases. If we have a lower attraction, then that would be a lower ionization energy. So those are the 3 points that I would hit when describing ionization energy going down a column. I would start by saying that as we go down the column, the atomic radius of the atoms increase due to the greater number of electron shells. This increase in radius causes the distance between the valence electrons and the nucleus to increase, which means the attraction to that nucleus decreases. Due to the lower attraction, it is easier or requires less energy to remove that valence electron. Thus, we see a lower ionization energy as we go down the group. Now, same idea, talking about going across a row. We see the radius decrease. Again, this is due to the fact that we are the same, they have the same number of electron shells and an increased number of protons. The shells are the same, but the number of protons increased, causing the atomic radius to become tighter, smaller. Again, according to Coulomb's law, this force of attraction between the nucleus and the electrons will become greater because the radius decreased. If this atomic radius decreased, that distance between the valence electrons and the nucleus decreases, then that means the attraction will increase, which would give us a higher ionization energy. Again, those would be the 3 points that I hit when talking about ionization energy going across a row. I'd say going across the row, atoms have the same number of electron shells, but the number of protons increases. This greater number of protons pulls on electrons more strongly, causing the radius to be smaller. According to Coulomb's law, when the distance between the valence electrons and the nucleus decreases, the attraction increases, which would require higher energy to remove those electrons. Thus, we'd see a higher ionization energy. Okay, that's what they're wanting instead of just saying the trend. You can't just say going from left to right that the ionization energy increases. You need to explain why, according to atomic structure and Coulomb's law. Okay, great. Okay. I'm going to explain this group 2 and group 13 counterpoint for ionization energy, as well as 15 to 16. We're going to do this in class. Okay, so I'm going to explain this in class. So, last concept, and that's successive or additional ionization energies. Okay? I like this one better. Look at this. This is saying that there are at least 5 electrons, maybe more, but there's at least 5. So I know I have some positive nucleus, and I've got at least this going on, okay? Now, the amount of energy it would take to remove this first valence electron, this is ionization energy 1. And for this guy, apparently that was 577 kilojoules of energy to do this to a mole of these atoms. That's why we have per mole. We know that when we remove an electron, that the entire radius gets smaller. So imagine with me that these guys and these guys, after that's removed, they pull in a little bit tighter. To remove the next electron, it takes more energy then. So it's going to take a little bit more energy. This is ionization energy 2, which was 1,816 kilojoules per mole. Okay? Yeah, okay, nice. I was worried I had this drawing a little off. And so it took a little bit more energy to remove the second one, because once we removed the first, they all pulled in a little bit tighter. And then here's our third ionization energy, which is a bit bigger. So this is ionization energy 3. To remove the third one, it took 2,745 kilojoules of energy to remove this third electron from a mole of these atoms. Now, I want you to notice something. Going from the third to the fourth, we see a huge jump in ionization energy. That yes, it increased from first, second, and third, but then there's this huge jump to the fourth ionization energy. And the reason why is because we must have grabbed all of the valence electrons, and now we're moving to a closer electron shell. When we go to these electron shells that are closer to the nucleus, when we make that jump from one shell to another one, we always see a huge increase in ionization energy, like a disproportionately high jump between them. So this ionization energy 4 was 11,577 kilojoules. So that must mean that this atom had 3 valence electrons. And I know this because the jump from the third valence electron to the new energy level, the fourth, was noticeably larger. That jump was much bigger. Okay? Well, reminder, any atom in group 1 has 1 valence electron, and when it forms ions with a +1 charge. Any atom in group 2 has 2 valence electrons, and when it forms an ion, it forms ions with a +2 charge. Any atom in group 13 has 3 valence electrons, and when they form ions, they have a +3 charge. Then we get 4 valence electrons, 5, 6, 7, and 8 valence electrons. All right, lovely. Now, the charge we know when they form ions, group 17 is a -1, 16 is a -2, 15 is a -3. Now, for this particular question, it says, based on the ionization energies of element X given in the table above, which of the following is most like the empirical formula of an oxide of element X? So we just found that X has 3 valence electrons. 1, 2, 3 valence electrons. So if it forms an ion, it's going to be a +3 charge, 3 plus. Now, if it's ionically bonding to oxygen, oxygen forms ions with a 2 minus or -2 charge. And so if we get this empirical formula, we crisscross the numbers for the subscripts. A 2 and then a 3. And so that's why the answer to this one is C. Okay. Good work, everyone. We'll keep practicing this in class.